Okay, so hello everyone. Welcome to our this week Rigorous in Vision AI seminar. And today we are very honored to have Professor Vijay Janapa Reddi to give this talk. Professor Reddi is currently associate professor at the Harvard University, VP and a founding member of MLComs, a non-profit organization aiming to accelerate machine learning innovation for everyone. He also serves on the MLComs board of the directors and is a co-chair of the MLComs Researches Organization. He led MLperf Inference ML benchmark for data center, edge, mobile, and IoT systems. I believe everyone knows the MLperf. His research sits at the intersection of the machine learning, computer architecture, and runtime software. He specializes in building computing system for tiny IoT devices, as well as mobile and edge computing. Dr. Reddi is a recipient of the multiple honors and awards, including the National Academy of Engineering Gilbreth Lecture Honor, IEEE TCCA Young Computer Architecture Award, Intel Early Career Award, Google Faculty Research Awards, Best Paper Awards at DAC, Micro, HPCA, IEEE's Topics in Computer Architecture Awards. Being inducted into the Micro and HPCA Hall of Fame, he's passionate about widening access to applied machine learning for STEM diversity and using AI for social good. He designed the Tiny Machine Learning TinyML series on edX, a massive open online course that sits at the intersection of the embedded system and ML that thousands of global learners can access and audit free for cost. So now let's welcome Professor Reddi to give us this talk, Democratizing TinyML.
Awesome. Thank you, Bill. I assume you can hear me well?
Yeah, we can hear very well.
Great. So I'm excited to be here today. I'm excited to be talking to you about TinyML. I basically have two key things that I want to get across today in the talk. So obviously, first I'll kind of talk about what TinyML is and so forth, but fundamentally then I want to help you kind of think about things systematically. So I'm going to talk about TinyML from a model sort of a standpoint, thinking about TinyML models and whatnot, the usual stuff around building machine learning models, deploying them on embedded devices, what are the challenges and so forth. And then another half I'm going to talk about is not so much about the models, but I'll talk more about the data because I think that's the next big frontier in machine learning systems. And TinyML specifically is really kind of interesting in this context because you don't tend to have big data sets like ImageNet and so forth. So with that said, let me first get started by talking about what is TinyML, just so you and I are basically on the same page. TinyML, I would argue, is one of the really fast-growing fields within applied machine learning, where we're really talking about intersection between embedded algorithms, machine learning algorithms, embedded hardware, and embedded software. And the whole reason that we're excited about the space is because we want to do on-device sensor analytics. In other words, look at sensor data and then think of doing the data processing right there by the sensor, rather than the traditional IoT model where we would actually take the data from the sensors and move it up into the cloud, and the cloud basically does all the big ML stuff. Instead of moving data to the cloud, what we're effectively talking about is moving the compute down to where the data is. And there are good reasons to do this, because from bandwidth, latency, reliability, energy efficiency, data privacy, and so forth, there are lots of reasons like that fundamentally want compute to be really close to the data. And one of the key goals around TinyML is that we want to do these things with ultra low power consumption, because we want to run machine learning all the time continuously. And ideally, we would be able to run these devices off of battery-powered systems, right? Rather than having them be tethered into the wall. And there are many good reasons as to why you want a battery-powered operation, because then you can actually deploy things out in the wild, wild west, and then be able to have intelligent sensing happening continuously wherever you are. But perhaps the most common example of TinyML is really the one that you and I take for granted, where, for instance, you're talking to the smart device and you say, hey, Siri. Now that keyword, Siri or hey, Siri, is sort of like the TinyML portion, because there's a small little embedded machine learning model that's actually running on the smartwatch that's able to detect. And once that system wakes up after recognizing the keyword, then we go into the traditional ASR pipeline of trying to figure out what's the speech, and then doing speech tech STT, and then later doing TTS, for instance. So this is where we largely are today, and increasingly what we're seeing is that we're moving into a space where there are lots of devices all around us, and the whole notion of TinyML is about how can we get these everyday devices that are around us, be it your toaster, your oven, your light bulbs, or whatever device it is, right? Rather than kind of dealing with manual touch interfaces, could we potentially change the way we interact with devices in the next generation, right? And I think like that's a really exciting space, because for a long time we've been dealing with touch interfaces, but I could totally imagine in the future, you'd pretty much walk up to a machine and then just talk to the machine. Now you don't have to have a full-on complicated use case, complicated speech pipeline running, because for instance, your toaster doesn't need to understand full-on English like what I'm talking about now. It just needs to understand a few commands like on, off, what temperature, or what setting, and so forth. That's like a limited vocabulary kind of context. And so there's a lot of excitement around this potential, and the industry is really looking at this. This is in the consumer electronic space, but also in the context of smart industrial manufacturing, for predictive maintenance, embedded healthcare, for personalized healthcare. There are lots of really interesting applications coming about because you're starting to do a lot of things with sensor device. Now, pushing things forward, like one of the interesting things that's also happening at the cutting edge is sort of like deployments of machine learning onto tiny little embedded robots. So I'll just kind of play this video from some work that we have done recently that talks about how you're actually using ML on small little nano drones as a cutting edge kind of an example about what's potentially coming down the pipe. Stop here because this is the key nugget down here, right? So there's a small little nano drone that fits in your palm, and as you can see, the computational horsepower on this system is really, really small, right? It's a microcontroller class processor. It's a Cortex M0 or Cortex M4 here, with only about 168 megahertz, very little amount of RAM in the order of a few hundred kilobytes. Now this is a pretty stock TinyML kind of a system, right? It's not about like having big models. On this particular case, when you're running the deep RL neural network policy on device, the thing is that it's doing is it's avoiding obstacles. It's finding a certain light source. It could be a gas source, which is the video on the right. And which you're also effectively having to fly, the nano drone itself, right? You have to kind of like keep that whole thing up and running. So there's a lot of just control processing actually happening because you're taking in inputs that are coming in from the laser rangers and the optical flow deck, and you're doing all that computing. So all of that computer has to happen in real time with the closed loop feedback system, right? So that's where some of the interesting challenges lie in actually getting the machine learning models to fit under these resource constraints and being able to do so under real-time constraints, right? And on the right, you can watch this video later on when I provide the slides, but basically it's taking this single drone and then scaling it out to a whole bunch of different drones. Now, these are just examples of, stuff where TinyML is kind of really pushing at the frontiers because you're looking at low-cost robotics, which has huge applications for search and rescue, those kinds of applications where you really want cheap robots that you can actually, that are quote unquote disposable effectively. If they break, it's not a big deal, but you can have a whole fleet of them going out. And there's some really interesting work that's actually happening at ETH Zurich with David Scarmaz's group and Luca Caroloni, who have been doing some really interesting work in this space as well. But these are some really, emerging application areas, right? So there are a whole bunch of different kinds of applications. And the whole reason that this is so an interesting application domain is really because sensors are all around us, right? It's a rich array of different kinds of sensors. You have motion sensors, you have acoustic sensors, environmental sensors, biometric sensors. There are lots of small little embedded devices that are around us that really are just dealing with sensor data. Now, if you kind of take a look at like all these tiny little, IoT systems that have all these sensors, they produce an insane volume of data. Now, if you kind of look at the stat on the right, it's basically saying that today we're using less than 1% of all of that unstructured data, right? What that means is that, like, if we're all excited about the possibilities of what machine learning and AI is doing today already, then imagine, if we can tap into this wealth of data, imagine all the rich use cases that we can open up. There's a whole ton of different use cases in my head that I can kind of start talking about because the industry is just so large in the context of TinyML. So there's a lot of excitement around this space. Then what are the interesting challenges for us, right? So I'm going to kind of get you to kind of think about two thematic things. So first is what I'll talk about is like around the context of like, what's a model-centric TinyML is what I'll call it. And another is being the data-centric sort of TinyML. Now, the model-centric side of TinyML is going to talk about what are the challenges that we get into when we actually want to deploy TinyML at scale. More often than not, when we talk about building models, we often end up deploying it into a single embedded device, right? But it's very different when you actually try to deploy TinyML models on one device and then try and port it over to another device. This gets into some serious scalability issues, which is a fundamental limiting factor. And so, we need to think about what does it mean to be able to deploy, TinyML across a fleet of embedded devices. And next, I want to talk about like what I call as data-centric TinyML, which is really focused on the data side of things. Like, TinyML suffers a lot from not having big data sets like ImageNet, for instance. Like, you can have those, but that's not representative. What's the ImageNet of TinyML is the key question that I often like to ask. Because when we're dealing with sensor data, what is that poster child data set that everybody should be looking at? And there's nothing like that. And so then I'm going to talk a little bit about how we should be thinking about data sets in the future. All right, so starting off with the model-centric viewpoint. It's all about deploying models. One of the beautiful things about TinyML is that the ecosystem fundamentally already exists out there in the real world. It's not like I'm saying, oh, let's go build this cute little AI accelerator, then we'll deploy them in the world and it'll be awesome and it's going to change the world. No, that's not what I'm saying. What I'm saying is that the existing substrate already is there for us. There are over 250 billion microcontrollers that are already out there today. And by next year, we're going to be shipping 30 billion microcontrollers in 1 year, right? It's staggering if you look at the rate at which we're growing in terms of the deployments of these microcontrollers that are found in autonomous vehicles, or even as a regular autonomous, regular car, for instance, is loaded up with different kinds of microcontrollers. And there are lots of different places, and that's where the volume is really coming from. And when you open the hood and you kind of take a look at these systems, one of the key things you'll find is that these embedded systems are really fragmented in terms of their capabilities. For example, like I'm showing you like a potpourri of different set of embedded devices here, and you can see that they all have like different clock frequencies, and they have very limited amount of memory. So flash is basically your storage, and your SRAM that you're dealing with is like really small in some cases, right? In the Arduino, for instance, if you look at this particular MCU, you only got about 256 kilobytes of RAM. Now you got to try and fit a model into that. And by the way, remember, a model is just one piece of the pie. Often you're trying to deploy an application on the embedded device, which means the model doesn't get the full 256 kilobytes. You might only, in fact, get about 120 kilobytes. So you got to kind of keep that in mind that you have some extreme constraints around. But more importantly, the point that I'm trying to emphasize here is that there's a lot of variability in the clock frequencies, lots of variability in terms of the memory capacities. Given that they're small, you've got a lot of variation. So what this means is that now if I come up with a model that's fitting on one device and I try and port it over to a different device, I can very quickly get myself into a pickle because it won't work. And this is quite a unique problem to the embedded ecosystem, because traditionally, in the mainstream ecosystem, like with workstations and servers and laptops and so forth, you don't have this problem. Because you tend to have fairly good amount of memory. The systems are fairly similar. In other words, there's enough capacity at large that you don't run into this sort of a problem space. So let me try and break that down further into the hardware challenges and the software challenges. On the hardware side, embedded systems often struggle from the fact that there's a lot of heterogeneity in these systems, right? So some of them have, only Cortex M class microcontrollers, which might be an M0, an M4, M7, or M33. However, even if I say I have a Cortex M0 processor, doesn't really mean that the ISA is exactly the same. In fact, you will find that the ISA, even between different chips of the same family, will actually have different ISAs. So what this means is that the code that I generate onto one embedded device is not easily portable into a family, into the exact same family. There's no guarantee that the models that you're deploying here will actually run on another device. So that's the heterogeneity aspect. This is not just about inside a Cortex-M class microcontroller. Then you have to deal with things like DSP engines, for instance, right? And the DSP engines also have ISA fragmentation, instruction set architecture fragmentation. And of course, now you're increasingly seeing like things like micro NPUs from ARM, which are like specialized neural processing engines. But then, however, those 250 million microcontrollers that are out there in the field don't really have the NPU. This is for the next batch of systems that are coming down the pipe, right? So you get into this problem like, any code that I generate might not actually be portable because of the rich heterogeneity in the ecosystem. Then, of course, I already alluded to the point that you tend to have really tight resource constraints. So you have memory constraints, you have power constraints because these are embedded devices. So you have to deal with those constraints. On the software side, you and I probably never think about allocating memory as being a big issue on a traditional system, right? You just say, okay, I'm going to call it something like malloc, and it's going to give me memory. I'm going to have heaps, and then I'm going to have a defragmenter to manage the memory system and all that good stuff. Yeah, well, these embedded systems don't have any of that luxury that we have in traditional desktop environments or server environments. And also, you can't assume that libraries that exist on one class of embedded devices are actually available in another class, which means I cannot rely on library functions like printf, something that virtually every system that's on a Linux system or Windows systems basically supports. You can't assume that, right? And you also don't even have guarantee that you will actually have an operating system. In some cases you might, some cases you won't, because you're trying to keep the system very lean in terms of computational requirements, right? So this is why you don't tend to have all these fancy features. Therefore, you get into this trouble. And then the question that comes up is, how do I deal with this fragmentation? If I want to be able to really realize the potential of TinyML, what I've got to be able to do is to actually scale this out, right? It's got to run across a whole fleet of different embedded devices out there. That's the only time when we'll actually be able to tap into that remarkable potential that's out there. And that's what leads into this discussion around TensorFlow-like micro. So at this point, what I'm trying to do is I'm trying to pivot into, okay, I've kind of given you a high-level overview of what the fundamental problems are. And TensorFlow-like micro tries to deal with those problems. And I'll talk about what we did here. So in TensorFlow-like micro, one of the key things is that you realize that typically when you have heterogeneity and fragmentation in the ecosystem, one type of code generation, quote unquote, that works well is an interpreter-based design. Right? Interpretation basically means executing a program following some sort of data structure that's stored in memory, as opposed to a purely compiled approach where the instructions are kind of predetermined ahead of time, right? You compile the code down. So in our case, basically what we're talking about is you want to save the model, not as code, as instructions, which is typical. Instead, you want to save it as data, and then you want to loop through the model's operations at runtime. And then that way you can basically make the necessary dispatch calls to invoke whatever corresponding operator you're trying to run. If the graph says, okay, I want a convolution, then you'll go, dispatch it to run the convolution. Now, this is quite in contrast to the traditional, compilation approach, right? Normally, when you're talking about efficiency, you tend to compile things down. Interpreters are inherently notoriously slow. If you look at something like Python, it's up to 70x slower than C. But given all the challenges that I mentioned earlier, you should be asking me this question, which is like, I thought you said we have resource constraints, we don't have good performance capabilities and so forth. So why would I ever want to use an interpreter-based design in order to implement the inference framework in order to deploy models on these devices? Well, that's where you have to make a very simple observation about ML code characteristics. ML code is inherently different from other languages. In other words, like, for example, if I have an instruction like a convolution, right, which is part of your neural network graph, that one quote unquote instruction or that operator is actually going to run for millions and millions of cycles, right? What this means is that reading the model as data and then dispatching it to the runtime op, that overhead, which is notorious in traditional interpreter-based languages like Python and so forth, is not a big problem here because that overhead is very small compared to the amount of time you're going to spend inside the operator. And that is effectively what allows you to realize that, okay, across any given network, that dispatch overhead to dispatch across all of these different operators is going to be relatively small in the big context of a neural network graph. And therefore, an interpreter-based design actually lends itself real nicely with very low overhead, which is what I'm showing you here. For example, if you take any kind of stock models and you look at the performance overhead from the interpreter-based design, then the interpreter overhead is remarkably small. Now, I'm going to jump the gun because I failed to mention one thing. Interpreters are great because they give you portability and flexibility. That's what's really nice about interpreters, right? Because you're not compiling the code down to a specific embedded microcontroller. Rather, you're letting the interpreter sort of like, do the execution of that. That gives you the portability and / flexibility that allows us to deal with the heterogeneity aspect that I mentioned earlier, right? Because the interpreter allows you to kind of run the model without recompiling the code for every particular embedded device. And also, in many cases, like you might sometimes have multiple different models, and what you want to do is you want to reuse the code. If you compile the code down, then you would actually have code bloat because the same operator would appear multiple times from multiple networks that are running on the embedded device. Now that, given that it's memory constrained, you really want to make sure you don't find yourself in that pickle, right? So if you use an interpreter-based design, then you can actually reuse the code, which is wickedly awesome. So what this means is ultimately what I'm trying to get you to understand is that, interpreters allow you to get the portability and allows you to reuse a lot of the code across multiple systems, which is wickedly nice. And that deals with the fundamental fragmentation problem, right? Now, I know it's like a very quick overview of a very complicated topic, but what I'm trying to get you to kind of understand are like, what are the fundamental nuggets that we had in terms of this design, right? Where you want a really small binary footprint. You don't want to rely on dynamic memory allocation because there might not be, by and large, dynamic memory allocation doesn't exist on embedded systems. You don't want to depend on any kind of libraries. You want to be flexible and portable so you can easily move across different embedded devices, with transparency in some capacity. And you don't want to rely on operating system level support, right? You need to be able to run bare metal. And TF-Lite, basically, TF-Lite Micro specifically allows you to kind of deal with this. Now, this is one approach. I'm not preaching that everybody who's doing TinyML should go and do, a TF-Lite Micro. Rather, what I'm trying to use TF-Lite Micro to communicate is that there are certain principal characteristics that we have to deal with, which is the embedded heterogeneity on the processor side. We got to deal with the fact that they have very tight resource constraints. Then on the software side, we've got to deal with the fact that we don't have library dependencies. We've got to deal with the fact that we don't tend to have operating systems. It's a totally different thing to deploy ML on embedded device as compared to all the cloud ML, all the mobile ML stuff that's been done over the past decade, right? So this is sort of the new frontier space that we're really wanting to push into. So one of the other things that I do want to touch on is sort of like, let's assume that we create this ecosystem where we're able to nicely run models on multiple different devices. Then how do I know as an end user? For example, I come to you with two different systems, right? Like these two embedded devices, and I say, hey, which one should I pick, right? Assuming that we now have frameworks that can deal with the kind of complexities that I mentioned earlier. This question of which one do I pick is very hard to answer because you want the system to be efficient. So how do you pick the most efficient system? Well, it's really hard to get to that answer because the machine learning system stack is inherently complicated, right? If you do anything in machine learning systems, you know, like, you can go from anywhere from there are many different applications, meaning there are many different types of machine learning tasks. There are many different data sets, people can use to evaluate their systems. There are many different models you can choose and many different optimization frameworks that actually get the performance at the lowest levels of the system stack, right? The embedded system ecosystem has something like this. The mobile ecosystem has something like that. Like the data center and edge systems have something quite similar to this, right? The specific tools might change a little bit, but the fundamental stack, the flexibility of the variability that you tend to have across the stack, is really, really rich. In other words, if I have a data point here, how I got to that data point is going to be really hard to know without knowing, what particular pathway you took. And that pathway is actually going to have an impact in terms of reproducibility. So if you want to understand which ML system X or ML system Y is better, then you need to know a lot of details about what actually is the task. And that's where benchmarking comes in. So benchmarking effectively allows us to, compare solutions, right? Different types of solutions can be compared. You can make an informed decision because you know exactly what the specifics were in order to get to a certain result. And that allows us to measure forward progress. Is system X better than system Y? But to do this, we need a systematic methodology, right? You need to have a rigorous methodology and you need a community that actually believes in the benchmark. If we can get that, then we get standardization across a variety of different use cases. We have comparability across various kinds of systems. We tend to be able to do complex characterization of exactly which which layer of the system is actually giving us the maximum bang for the buck. And ultimately, we want verifiable and reproducible results, because without that, we can't make forward progress. And that's where I want to introduce MLperf, right? So MLperf is basically an industry consortium that kind of like focuses on 5 key principles that are shown here. The first one is to enforce performance result replicability, which is a big issue in ML systems. The second is to kind of like have a suite of representative workloads, meaning like, what are the good workloads that we should all be using as standard best practices to benchmark and evaluate systems? Because that tells you which workload classes are important. Then we want to encourage innovation and state of the art, which means the models have to try and push some of the hardware capabilities or the software capabilities. The ultimate goal of MLperf as a community is to kind of drive fair and useful measurements. And you want to have the commercial and research ecosystems. The second you bring in the research ecosystem, that means benchmarking cannot be something costly, because researchers like you and me, for instance, might not have wide access to all kinds of training resources and so forth. So you got to keep them accessible. Semiperf is this thing that we created back in 2018, which has become effectively the industry standard. And one of the key things in the context of TinyML, in order to democratize TinyML, we wanted to accelerate the pace of hardware innovation by systematically standardizing how we talk about what is performance on an embedded device. And that's where you'll realize there's a wide array of machine learning different tasks, right? That if you pick one task, you still have that full vertical stack that you're dealing with. So I've kind of shown you how I've kind of grouped them into different kinds of use cases based on the sensor modality, ranging from audio, image, telemetry data, and so forth. And within each of these, you have a lot of different use cases. And each of those has different kinds of neural network models you might use, right? And they can have corresponding different data sets. So the question then becomes like, which of these, like if someone comes to you and say, hey, check out my system, it gets this performance for inference as a TinyML device. Immediately I'm like, and someone else comes in with system Y and says, hey, check this performance out. Then my immediate question is like, I don't know, what are you running? Are you even running the same thing to say that the numbers are better or worse? That's why you need some sort of principled approach in terms of how do you systematically sort of understand what benchmark, right? So, what is the definition of a benchmark? This goes to the point about like, are you looking at a model's performance, or are you looking at an end-to-end application performance, which includes both pre-processing, post-processing, and all of that kind of overhead, which might not have anything to do with your machine learning model acceleration itself on the TinyML device. The second thing is, which of those tasks that I showed you do you actually pick to actually say, okay, I'm going to benchmark an audio task that's like keyword spotting or something. Then what exactly do you measure in performance? Are you happy with performance if I drop your accuracy by 50%? And so I'm like 50% wrong all the time because I did some crazy quantization with low numerics. Are you happy with that or no? It's like I say accuracy is minimum. This is the minimum accuracy that I've got to hit, because otherwise machine learning is basically useless, right? So certain accuracy target, what is that accuracy target, and how do you measure performance with respect to that accuracy target? You can't violate that accuracy. Then of course, when you're implementing things, I might have used a TF Lite engine. You might use something like, STM's toolchain, or you might use MicroTVM or any one of those different frameworks. So people often re-implement things. So you need to have a good set of guidelines about what kind of optimizations you allow, what quantization do you allow, retraining, and those kinds of questions. There's a lot of nuance in this, and I'm happy to talk about these more detail later on if you want. But you got to have a systematic approach. And MLperf, basically, one of the things that we did when we built MLperf Tiny was to kind of standardize around these kinds of things. And here are 4 representative workloads. Keyword spotting is something that's deployed in billions of devices out there, right? So it's a very big application area. Visual wake words is another way of effectively being able to say like, hey, is there a person or no person? That principle of detecting something is a visual wake word, detecting some kind of activity effectively. Anomaly detection is huge in industrial manufacturing, which is why TinyML is said to have the biggest market volume. So you can do predictive maintenance, be able to replace parts before the breakdown. And things like Ring, doorbell, and so forth tend to do some basic image classification, right? So these are the different tasks that we landed on. Now I just kind of want to talk a little bit at a high level about like, what does it mean to create an industry standard benchmark, right? It's a very complex thing, in all honesty. I like to say that the way you should think about benchmarks is like building a Hubble telescope in order to be able to look into, deep into the universe, to be able to ask some fundamental questions. You want to look up, sure, you can look up from down here and look through the clouds and say like, oh, I really don't see anything out there, right? That's because we haven't, we're not using the right instrument. But if you look through the lens of a Hubble telescope, you see a totally different universe out there, right? And so for me, benchmarks effectively, that's sort of a scientific instrument. You're building an instrument in order to, really understand, how a system is performing. And so to that end, you've got to be very careful in how you engineer the benchmark. This is not a Mickey Mouse activity where you just say, oh, I just take this model, I'll take that data set and I'll just run them together. That's not a benchmark. So that's the point I'm trying to get to here. There are multiple stages in creating the benchmark, right? So clearly the first one is what's the career problem definition? What task are you kind of looking at, right? What's that data set? Like, is that data set actually representative? In other words, like, does it have the right resolutions of the key characteristics you're looking at? What's the model that corresponds to it? Is that a model that if you were to study actually has meaningful insights? Or you, like, for example, like if you study AlexNet, right? I still see a lot of papers in the architecture community, for instance, using AlexNet. And I'm like, yeah, it's not so much about whether it's AlexNet or not. It's the fact that the model's characteristics can be quite different from what transformers look like, for instance. So if the entire field is really moving towards transformers, then are the architectural optimizations and considerations you're having here, are they really meaningful in this kind of new paradigm of networks that we're starting to see? That's that sort of fundamental question, right? Around that's why you got to pick the model very carefully. And then, of course, you have to have provenance, right? You've got to be able to read, know exactly how the network's constructed. So you got to have the model's original training code. Then you have to derive some sort of quantization because TinyML is all about quantized networks, right? So it's 8 bits, 4 bits, and so forth. You're not running FP32s usually. Then you have to have an embedded implementation, right? In other words, you have to physically deploy this. You need to package that and deploy it either through TF-Lite or some other framework. Then you have to actually have a harness that actually, starts and stops. Now that seems very simple, but it's not, because remember, an embedded device does not have many resources, right? So therefore, how you actually load the input data into the test system actually becomes quite a big problem, which none of the other bigger systems like Cloud ML, Mobile ML actually have. And then of course, you package and deploy it and you run it and you gather data, right? So you got to kind of stitch all of this for all of those 4 tasks that I showed you. And as the field is evolving, new tasks are starting to come in. And one of the key questions then becomes, right, after you do all that, how do you sort of measure what is good or what's bad, right? Obviously, latency is extremely key because you want to be able to say, like, how well is the, whatever processor or whatever embedded system you want to compare, system X versus system Y, latency is a key thing. You're not often looking at throughput, right? So latency is a key metric. And again, as I said, you need accuracy. Accuracy is the minimum accuracy is the most important thing, right? Again, if 50% of the time you're wrong because you compromise your accuracy because you're using something like 4-bit numerics, then that's not a meaningful sort of data point to actually have, right? So you have to figure out what's that minimum accuracy. And this is where industry consensus actually helps quite dramatically in understanding what is a meaningful metric. And then of course, you have to usually measure energy, right? If you don't measure energy, then it's just, these are TinyML devices. So you really have to measure energy. And MLperf Tiny basically does all these 3 things. Now, I forgot to put a link for the paper, but there's a NeurIPS paper that we have on this that talks about like how we actually engineered the benchmark, what went in, and what are some of the interesting lessons learned. While I've shown you those kinds of existing applications, one of the things that I do want to mention is that there's a new genre of applications that are coming out, and hopefully we'll have a paper out on this like later this year that talks about new sets of networks that are coming in. Even in TinyML use cases, you see multi-DNN workloads coming about. In other words, in multi-DNN, you have things like pipeline networks, concurrent and pipeline DNNs. A pipeline DNN is basically saying, hey, I have one network running. That one network, if I detect the keyword, I might have to trigger another network. That's a cascade. So in other words, you've got like, back-to-back pipelines of like these things running together. You might have concurrent networks. For example, if I have a smart glasses like what Meta is trying to build, then I might actually have multiple networks that I have to concurrently run at the same time. I've got to do vision processing. I've got to do hand tracking, gesture recognition, and all those kinds of things. And sometimes I might have to do a mix of both of them. So the point that I'm trying to make here really is that there's an entire new genre of workloads coming about that are going to help push the embedded system development to the next level. Now, boiling back up, the key thing that I'm talking about now is kind of like really focused on like, model-centric things, right? I talked about some of the challenges in deploying TinyML at scale, because I really think as much as people are excited about it, they don't often realize just how difficult it is to scale things out. That's one. 2 is actually having a deep appreciation for how do I compare these systems? Because if you want to accelerate the field, quote unquote, democratize TinyML, then you need to have those pieces on the model side. The other half, of course, is this question about data. Where does the data actually come from in order to train the models that we can deploy across a heterogeneous fleet and then push them out in the wild? We're all very excited in talking about models, but we don't talk about the elephant in the room, which is actually the data sets. And that's where data-centric, TinyML is. Let me talk about data-centric TinyML in the context of like keyword spotting or wake words or hot words. It's called multiple things, but the key thing is you've got some kind of keyword that you're looking for. And often when you look at a lot of the voice assistants that we have around us that we take for granted, right? The Alexa devices, Siri devices, you find that they don't support multiple languages. My mother tongue is actually Telugu, which is an Indian language, right? And there's no chance that there's an Alexa or a Google anywhere on the planet that actually understands, my mother tongue, right? Even in limited vocabulary, in other words, even in just like small words, right? So if I say namaste, yeah, the machine's not going to wake up, right? For instance, but the idea is that like we should be, when we're talking about speech, we should be thinking about how does these technologies work across different kinds of languages. And I'll talk about why that's a real big problem. And especially in TinyML, given that keyword spotting is sort of the one of the killer applications, we really got to think about how we can address that. One of the key challenges is that there's so many different languages out there, right? So there are over 7,000 different languages spoken on this planet. And when you look at data sets, which are needed to build those models, as you look at more and more languages, you find that the data sets basically disappear, right? The data sets just don't exist. The question is like, if we use the existing model and method of actually manually going and trying to build data sets, AKA data engineering, where you have to gather the requirements for, okay, what kind of keyword am I looking for? Then actually go and manually have people gather the data and then go and, there's no guarantee that the data that they've captured is actually correct data. Maybe they incorrectly labeled yes as no and no as yes. You've got to do data cleanup, right? Then you've got to keep improving that data. You got to repeat this whole process over and over. Now, this process is very tedious in reality, right? It's an extremely tedious process, but this is one of the limiting factors of today's machine learning, because this is the state of the art in some sense of how we build, data sets, be it TinyML or otherwise. Especially in TinyML, this becomes really problematic because in some languages, for instance, when you're talking about doing keyword spotting, in some languages, you don't have that many speakers. So being able to manually go and collect this is not something that you can do. You can easily get, something like English, you can easily get a large number of people who can contribute to that, but that's not always the case. This is where I argue that we have to have a fundamentally different approach to how we think about data sets, right? And I'll talk about this in the context of the multilingual spoken words corpus that we released late last year, which is basically a data set that was quote unquote automatically created, right? That's a keyword. It was automatically created. We did not actually manually go and collect anything. And just to demonstrate the technology, we chose 50 arbitrary languages. And we built a data pipeline that allows us to magically create data sets, which basically leads to over 23 million audio keyword examples, right? So it's an insane corpus. Just to kind of put this into perspective, the state of the art is usually, I would argue, like speech commands, Google speech commands, which is basically in English, and it only supports, originally only supported 10 keywords, and it had, later got extended to 30 keywords, and it's basically been there for a while. Instead, like the spoken words basically extends this out to many different languages that I'm showing you here. Now, the data distribution across this is not uniform. In other words, there are some languages where we have a lot of data, and there are other languages where there's little data, but that's still okay. I'll talk about that later. In many cases, because we built an automated data engineering pipeline that I will talk about, we were able to create the first time, we were able to create data sets and languages that previously did not have any machine learning data set in terms of limited vocabulary. And what this means is that now we're able to, if you look at all the languages we put together, that's spoken effectively by 5 billion people on this planet. And we were able to do this only because we built an automated data engineering pipeline, where we have lots of different keywords in each of those categories that I mentioned earlier, right? And lots of different keyword samples. So a keyword is like yes, no, by, boy, girl, and so forth. And the samples is how many of those kinds of clips do I actually have, right? So at large, it's like, over 340,000 keywords, 23 million samples, 6,000 hours of stuff. This all sounds great. I promise you there's something negative down here that I'll get to. So the way we kind of did this was by systematically rethinking about what does it mean to build data sets. So let me use an analogy down here. The internet, let's talk about Google search, right? So when we talk about Google search, what did Google do? Did they go out, index the entire planet's, all the web pages on the planet, and then say, okay, we're done, right? Did they do that once? Or did they build a pipeline or a computing architecture that continuously searches through all of that, data? Some of the websites are great. Some of them are just raw junk. Some of them are so old, you don't even care about what's on that content, for instance. Do they care about that? No. First, what they do is they built an engine that allows them to continuously keep creating this massive corpus, because the truth is data is not static in the way we've traditionally thought about it. We tend to think of data as a static entity, like a data set. No, that's a version, if anything. Data is continuously live, right? It's continuously changing. It's drifting all the time. So what you need is a system that can actually ingest data continuously. And then you have something like a PageRank algorithm, where the algorithm effectively then finds the needle in the haystack that is of interest to you. And that's the exact same vision that I borrowed. And what I'm trying to show you here is that there's lots of audio data that is out there, where you have a certain audio clip, for example, that has all the spoken, like for example, this video has got audio with it that's likely going to get transcribed. So there's a text transcription that's often associated with it. Now I'm talking about movies, songs, just TV shows, and there's a lot of content out in the wild there. So what we did was, like, we basically said, hey, can we take all of that data that's kind of out there, and can we create a pipe where we ingest all of that data and automatically use forced alignment, which is a well understood technique, where we basically chop up the audio signals that are out there, right, into small chunks. And effectively, each word is kind of bucketed into individual points, and then you select the particular words of interest to you. So imagine you go in the future and you go to a web page and you say, okay, I want a TinyML model that can recognize the word bank, bake, temperature, some number of digits, and then that's it. You don't worry about the data set. You don't create a data set. The data set is generated automatically, because the system goes and finds all of these little audio clips out there, and then you push it into a training pipeline, which is the boring part, honestly. That is a whole model-centric kind of stuff that I was talking about earlier, right? Which we all know how to do. And if you can do this, then that's how we created this massive corpus, right? The multilingual spoken words corpus. This allowed us to suddenly kind of scale to a large number of languages out there, right? So over 50 different languages was the first shot that we gave. And there's over 340,000 audio clips and all that good stuff. Now, I did promise you that I will talk about something negative about this, right? Which is, this is great that we did the first step of creating a massive corpus. Now, when you go in though, inside the data set is not picture perfect. In other words, it's not clean. It's not like someone sat there and verified every single sample. You can't, because it's just so big. So that brings us into phase 2 of how we need to be thinking about data sets, which is essentially thinking about it as algorithmically, how do you sort of filter through that massive corpus? Because there's good data in there and there's bad data in there. Well, what we need is a second phase of, like, can I build algorithms that are able to go in and then be able to very quickly sift through that huge corpus and find the right set of samples. Now, remember, the right set of samples doesn't necessarily mean the cleared word bank, for example, right? That's me nicely saying bank. But in reality, there might be background noise, right? Imagine, like, if I'm watching TV and I want my TV to, if it's triggered by the word bank, I need to have background noise and background sounds and all of that included. You need a system that can actually have all of that as well, right? So what we did was we basically, there's entire mixture of background noise that you'd automatically be able to pull in and fold into the system. But you need algorithms that can do that filtering. So we did some work in that New York's paper where we talk about how do you do this kind of filtering. But the point I'm getting to is, we need to start, quote unquote, benchmarking data. In other words, we need to come up with mechanisms that, the way you can compare, hey, what's, is model X better than model Y with MLperf? We need something that will allow us to look at, data quality effectively. And that's where I'm going to talk about Dataperf, which is one of the things that we're actually actively working on now. As I mentioned earlier, I mentioned MLperf to you because I wanted to talk about the fact that what we did was, historically, when we want to know if system X is better than system Y, we're going to compare systems here that are optimized for ML, but we freeze the data set, we freeze the model, right? We tend to say, like, okay, hey, I'm really just interested in the model's performance. I don't care about the data set. So just kind of lock those, and then, let me kind of see what the infrastructure can do. But now what we increasingly want to do is, like, And then we have things like Kaggle that kind of look at, what's the, you can focus on optimizing the model, right? So MLperf focuses on optimizing infrastructure while freezing data in the model. Kaggle says, I don't care about the infrastructure, I'm going to freeze the data, and really I want to look at the model's performance. Our question is, can we create something new where we want to optimize the data, where we're freezing the model and we're freezing the infrastructure, and we really want to drive data quality in some sense? And if you kind of look at where we all are in the existing ecosystem, I'm looking at the publications over the past couple of years, right? And what we're looking at is a massive increase amount of papers that are getting published, but all of these papers are really focused on the model-centric viewpoint. They're not talking about data at all, right? So it's only last year that the community is increasingly thinking about data. Now, this is nothing totally new. There are a few people who have been working in this space for a while. And what we're trying to do is try and bring light to that, right? And the reason for investing in data is because if you don't invest in the right data, you can come up with models that are just garbage in, garbage out, right? And you can feel great about having a New York paper that actually does nothing, because all of that work is effectively wasted, because you can't just take that model, because the data that it was trained on was actually not representative in some sense. And that's what I'm trying to show you down here, right? With the Tacoma Bridge, for instance, like the problem that we had was that the civil engineers missed the fact that at certain high winds, you tend to have the resonance issue that they didn't test for. And therefore the bridge basically collapsed when that happened in the real world. This is the problem with data, right? If your data set is not reflective of what the real world data truly looks like, then you've got a problem, because you're going to push this model into the wild, and boom, the whole system basically blows up in your face. And that's going to be a problem. Now, just to kind of make things a little dramatic, imagine if this was the case where, I'm trying to detect whether you have cancer or, a brain tumor or something like that. And imagine I say, oops, my training data set was not as good. That was a researchy data set. But in the real world, yeah, I kind of missed that tumor as a doctor. And so, yeah, in 5 years, you show up and you're like, bam, I'm out. So it can be pretty bad, right? Think of an autonomous car, same thing. If your data set is not good, then the car is likely going to run over someone if it's using an end-to-end learning model or something like that. So therefore, it's really time to focus on data quality. Specifically, we really need to understand what's the quality of the training data that's actually being used on the model, and how, and then you train it, and then the test data, which is the litmus test that allows us to release the network into the wild, right? How good is that test set? How well are we architecting this, right? And then, of course, then there are going to be algorithms for constructing and optimizing the data sets. And this is where, for instance, I was talking about the MSWC, for instance, where I was saying that, we want good algorithms to kind of have a large data set, but then like really sift through it to try and find the right data set that's good for a particular deployment of the model. So the whole idea of Dataperf is that we want to measure model performance, we want to measure training data, we want to measure test data. But in order to do that, what we are focusing in Dataperf is really locking the model. In other words, we give you like something like ResNet 50, and you say, okay, you got ResNet 50, you can't touch the network. Now make that ResNet 50 architecture do really well for dataset X versus dataset Y, right? And so just by changing the data, in fact, the less data you have, the richer data you have, the better the model should be doing, right? Like that's what you're trying to find. What is the smallest data? And that's good, because now you can cut down your training time. If your data set is small, you can train the network really fast, right? That's one of the benefits you get. And also you get robustness in the data as you push this model out into the field. So the other thing is sort of like, you also want to focus on, So in order to do this, what you would do is you measure the training data by locking the test data. So you're locking the test data and you're locking the model, and you're only changing the training data. And similarly, you lock the model and you lock the training data, and then you change the test data set to see how well a certain test is doing, because you also want to know, is exam 1 good or is exam 2 better, right? Because that helps you understand how good a student, quote unquote, in a classroom has actually learned. And of course, there are different kinds of algorithms that you can get into, data splicing, selecting data, and all that kind of good stuff. There's a lot of nuance around here. And similar to MLperf, the idea is that we want to come up with different kinds of benchmarks. And I'm just kind of showing you a sampling of different kinds of things that you might be interested in, like training and test set creation of the data, right? The way MSWC was created, it was all automatic. Was that good or not? Training and test set selection. So for example, I have a big corpus. How can I select a smaller, rich data set, like a subset of that data that's actually really good for training? And then data valuation is like about, there's a marketplace for data. So you want to buy data set X, or should I buy data set Y? Maybe data set X You don't know what's inside the data. So how do you know if I spend 1 million or 10 million or whatever it is that data set really worth the money that you're spending? We don't know. We don't have answers to this because we can't put a number on data, and that's what we're trying to change here. And of course, this has to be done in the context of many different kinds of machine learning tasks, given, again, we have a rich heterogeneity of different kinds of tasks, right? So Dataperf is really looking at this intersection between what kind of tasks do we look at and what kind of benchmarks, core benchmarks do we have. Alas, I covered a fair bit of ground, but there are two key things that I was trying to land on today in the talk. One is model-centric, another is data-centric. In the model-centric world, what I'm trying to focus on is, hey, you know what? The embedded ecosystem is crazily heterogeneous. So if we want to quote unquote democratize the embedded ML or TinyML, we need to somehow deal with the fragmentation problem. On the data side, we need data-centric methods, especially for regimes where you tend to have small data. And I use the keyword spotting as an example to show you how, for example, even though you don't have existing data sets there, if you can build the data engineering pipelines and you can realize the vision of, hey, I can actually automatically do this. Now, we only did this for speech, for instance. One of the things that we're now shifting our attention to is in vision, can we actually do the exact same thing, right? So that's sort of the mindset that I'm pushing for. And in both of these, model-centric and the data-centric paradigm, what I'm trying to show you is that you need to be able to measure, benchmark things, right? Benchmarking is something fundamental. Because if you don't benchmark things systematically, then you can end up with garbage. Everybody saying, I'm better than you, you're better than me. And nobody knows who's actually better, which means we can't make forward progress if we go with that attitude. So we need to have the right scientific instruments in place, and benchmarking is a scientific instrument. And I talked about how MLperf can deal with the model-centric viewpoint and how Dataperf is dealing with the data-centric sort of a viewpoint. And with that said, I'm going to stop here and turn back to you, Bo, and I'm happy to take any questions in the last few minutes.
Thank you. Very, very inspiring talk. And actually, we already have one question in the chat box. So the audience asked question, we have used the linear models in many real-life predictive models successfully. Linear models are highly scalable and can be updated in real time. Or can we even add or remove models input in real time? For example, if we lose a few sensors, the model can be rebuilt in real time in your device. So the audience would like to know your experience with linear models in TinyML.
Yeah, so that's a good point. So I think as much as I've kind of hinted or kind of focused a bit on the deep learning side of TinyML, it is true that I think not necessarily focusing on deep learning based methods is actually quite useful. In other words, especially in TinyML, just kind of traditional ML is actually quite useful because it can also be computationally efficient. I mean, that's what I've seen in practice when I'm advising startups and so forth. But that said, you would also hear folks in industry increasingly saying, yes, that's all there, but deep learning kind of it simplifies some of the issues that we have in terms of dealing with noise in the system and so forth. And when we're scaling it out, it's much more robust to just kind of this, it's got some robustness characteristics just because you can train for that robustness inherently. And when you're deploying it at scale, that's sort of a nice little perk. And so what I've heard is that that's the reason increasingly, we're seeing a shift towards just deep learning based methods. Now, hopefully that answers the question side. I do think it makes perfect sense given the resource constraints to keep an open mind and not just focus on deep learning based methods and just traditional ML like SVMs, random forest, decision trees, and so forth. They're actually quite powerful.
Thank you. Any questions from the audience? You can unmute yourself.
I managed to put everyone to sleep.
Hi, this is Syed again. Can I just ask another question, if it's okay?
I'm fine, yeah.
My point wasn't about the actually random forest or GBM or even SVM, except the linear model of the linear version. Most the linear models, say, for example, even for the SVM, for the random forest, GBM, or any nonlinear and iterative models, say you build a device on a robot and send it to Mars, right? And this model is inside a device and using 100 sensors, right? And then you have a model which is working. We can talk about and for some reason, a few of those sensors now it's not working. None of models like deep learning or random forest or the GPM, they are not going to work because you cannot easily just remove some of them. However, the linear models like LDA, linear discriminant analysis, even PCA and the MLR, you can easily update the model if you lose those sensors. And I believe these features is very important. And even those lack of the nonlinearity can be solved by using the nonlinear feature extractor. For example, combination of convolutional layer to extract the features from the images and then add the linear discriminant analysis or QDA as the predictive modeling layer. Completely can add all those. We tested this one, we got to 99% of accuracy of deep learning. But those features, which I believe in the real life is much more important.
Yeah, so I can't say that like I'm not an expert on the algorithmic side of things. Let me prefix with that. I tend to think more of the system standpoint. I agree, like, yeah, in certain kinds of cases where if you're dealing with multiple sensors and so forth, it makes sense. And many of the use cases that I was at least referring to have been like, you're not really dealing with so many different inputs, I would say. And not to say that that is not feasible, right? And again, I don't think there's like any one solution that is the killer solution, right?
No, for sure. Yeah. There is. That's the reason we have many different cars, right? It means that's the.
Yeah. No, it's a very good point. I appreciate you bringing that up.
I think we have now questions.
There's another question.
Oh. I would like to learn about how to select a TinyML model to solve common computer vision tasks, such as activity recognition, segmentation, since there are too many models. Oh yeah, isn't that the problem? I don't know. There is no one silver bullet in this, right? Like, so, and this is exactly that sort of issue that I was mentioning earlier. From a performance analysis sort of a standpoint, we have this exact problem, right? You're asking about it from, how do I select a TinyML model? Again, I think this goes back to what's that specific task you're looking for and what metrics you're looking for, right? Obviously, efficiency is extremely key in this kind of a context, right? And so one would simply be just what we have done in practice has been just looking at the resource requirements. I do want to say that when you're talking about resource requirements, often like the resource requirements that are reported in terms of parameters and so forth that are reported in all the ML papers that are great. However, that doesn't actually tell you what the dynamic requirements of the network are going to be, because sometimes, like, the data movement that you actually have as a result of the operators that you're performing could actually result in, something where your parameter count might actually be more, but the way your activations are triggered and how you store them might actually be much more efficient in a seemingly larger network. So those raw metrics that are often presented are only one part of the story, but I don't think people realize that because all the intermediate tensors that you work with consume a lot of resources. I think like that's one of the big things to look out for when you're quote unquote trying to pick a particular model. Hopefully that answers the question, Panwan.
Other questions from the audience? So there's another question in the chat box.
Yes, question about on-device model training is also key to TinyML. Yes, on-device On-device training, I haven't yet run into any real-world use cases, to be honest with you, where I've actually seen like you really need on-device training. Do you need on-device sort of fine-tuning? Yes, absolutely. That's already being actively done in production use cases. On-device training, I'm still not fully convinced. I mean, a lot of people will immediately jump onto like asking me about on-device training or federated learning-based approaches. But one of the key things you have to, when you have to do that, is that you really have to close the loop, right? Because you have to have a good idea about what that model, when you actually do that on-device training, how is it actually performing? Closing that loop of doing continuous monitoring on these devices is not easy. It's something that we take for granted in traditional MLOps pipelines, right? But you can't do that with embedded devices. So while it's kind of an exciting topic thematically to kind of do research on, which even we are interested in, right? There are lots of concerns that I see in the production pipe where people are like, oh, I'm not sure I actually want on-device training, because that's like a micro optimization, which might not necessarily be good when you look at it from the big picture sort of a standpoint, because bigger systems often need to kind of understand how the whole fleet is doing, and you want that raw data to come back, which requires communication. The second you have communication, you're going to drain your battery, especially in TinyML devices. So therefore, I'm a little skeptical now to see like where on-device training is really going to land. That's sort of my academic perspective and industry sort of a viewpoint. Hopefully that answers the question. Oh, for sure. I also think it's a great advantage of retraining models to fit applications continually overusing a linear model. I think the retraining stuff, I think conceptually sounds good, but I strongly encourage people to kind of like really understand the MLOps. So let me share something with you. Share my screen again. Sorry, a lot of slides. Okay. One of the key things that you had to realize, right? Like as much as like, one of the key things to realize is that machine learning, when you put it into practice, is a very complicated pipeline. Very often people talk about coming up with a cute little model, putting it on a small little embedded device. We throw our hands up and say, hey, check out my awesome paper. Yeah, but that's not how the real world really works, right? The model development and all that stuff is just one tiny piece of the entire pipe you need to have in order to successfully deploy models into practice, right? You need to do ML training operationalization, have a systematic reproducible pipe. Then you have to do continuous training. In other words, you're dealing with data drift, model drift, right? Then you have to deal with quantization related effects that you get into before you deploy models onto the embedded device, which I kind of touched on a little bit today. Then you have to understand how these are actually served in the wild. Like, are you really doing just pure latency, or is it some sort of latency throughput kind of deployments? Then you have to monitor what the model's actually doing, because data is live in the field, right? So all of that, you need to have this complete pipe in order to be able to come back and close the loop. For example, you might do continuous monitoring and it says, well, I've got a lot of data distribution drift out in the field from what the model was trained on, which means then I have to go back, right, from here to here and then retrigger continuous training, which you can only do if you've actually built an operational pipeline in the ML training stage. What I'm trying to get to is that it's there's a lot of excitement often when we think about wanting to retrain and so forth, but in practice that retraining is very sophisticated, because it's not about just let me just retrain because I can get better accuracy, right? You have to go through the pipe of again doing the deployment and so forth. And when you're doing all this in practice, it's not you doing it. It's a team of MLOps engineers that are actually, the entire MLOps people doing it, right? That means you're going from a business analyst who's setting up the KPIs, then you have like data scientists, you have data engineers who are working with the data and actually continuously looking at the data drifts, right? Then you have ML engineers who are probably mostly responsible for training it and then actually deploying it. Then you have software developer people who have to deal with CI/CD flows, continuous integration and continuous development flows, because all of this has to be automated, right? The long story short, what I'm trying to get to is it's actually very hard to retrain something. It's great for us, like academically, we tend to say this, but in practice, it actually doesn't turn out to be that I can very quickly retrain. It's a very sophisticated process. And this is what big companies struggle with. let alone TinyML. I think TinyML is still far from understanding all of this. So as much as we are excited about retraining, all I'm saying is that like we got to understand the bigger picture. What does it mean to retrain in that? What if we build this complex pipeline directly into smartphones and MCU-based devices and also benefit from using smartphones? What I'm talking about, this complex pipeline that I'm showing, that's not a pipeline that you deploy locally, right? It's a mixture of development environment coupled with productionization, right, or operationalization. So this is not a single software block that we're talking about, right? So we can't. I mean, a CI/CD flow is not something that you would want to do on a mobile device, right? I mean, that's like having a fleet of different embedded devices and testing how the model will perform on it. And you have to do that because embedded devices have a rich array of different kinds of inputs. So you might say, I have a microphone. Yeah, but the microphone on device X is different from the microphone on device Y. So that sensor input, which the network actually picks up, is going to be, quite different. So it's not that easy to be able to take that complex pipeline and just drop it on a single device. I can get into a lot more about this. That in itself is a completely different talk, but these are good points though. And if folks are interested, I'm actually giving a ML Ops for TinyML talk in 2 weeks on the TinyML Summit. We're actually intend to talk about the next massive wave of, I touched on Modelcentric, I touched on Datacentric, and the third piece is really the operationalization of TinyML. And there are a whole bunch of technical nuggets in that space. If folks are interested, I'll let Bo know. Cool.
Other questions from the audience? I think the audience has a follow-up question about the federated learning.
Yeah. Federated learning, yes, it's a natural inclination of people to kind of think of in the context of TinyML and so forth. But again, like what I often like to say is how much are you going to burn on communication? Because federated learning makes you fundamental assumption that you're actually going to be able to send the gradient updates up, right? That means you have to have communication, which we cannot take for granted. In some cases, yes, it might work well. But in the context of some extreme deployments that people are trying to do, it doesn't really work in practice. And it's also been shown, and we have also shown it, like federated learning it's got holes, right? The fundamental concept is interesting, but it's also got, your gradients leak information about the actual thing. Federated learning plus TinyML may change the whole deployment. I'm skeptical about that, to be honest, and the reason is because I think the communication is going to be the Achilles heel of the system. If communication is not a big problem, and I know from like looking at real world devices that are in deployment, people will say 50% of that is just 50% of the energy is just dedicated for communication of battery life, which is kind of crazy. And if you look at how often they communicate, they barely communicate. And that's because they have to last for about 5 years or 7 years in the field. So what that means is that, like, and if you're talking about federated learning, retraining, and all of this, these are all computationally hungry kind of things. So this is where I get skeptical as to whether that's the right approach. I'd rather use that energy in the ML ops to do continuous monitoring with sensor up, right? Do continuous monitoring and then just do a better build and then do a single push down over the air update to the embedded devices from a tactical sort of a standpoint, right? Because then you have all the guarantees, you can do very good analysis and you're not randomly pushing models, or these models are not randomly changing their behavior on the field, and then you have no idea how they're actually performing at the endpoint, right? Because the model that you pushed is not what the model is actually doing. The model is doing something different. So that's why I'm a bit skeptical about it. Not to say that we shouldn't do work on it. We don't know all the answers, right? That's why we should do the research on it.
Other questions from the audience? So actually, I have a follow-up question. So So you just mentioned about that about 50% of energy is from the communication. So that is because of the wireless communication.
Mm-hmm.
Or
Yeah.
And
Yeah.
the embedded device, right? Because for the federal learning, we have the different types of scenarios that so the devices they may be connected via the line or the wireless, or and also it may be the kind of the desktop as the device or just the embedded device. So I was wondering, so for the communication, the retraining cost, so is it kind of still feasible for the, like, if we connected the multiple desktops, something like that?
I mean, yes, but then it's not embedded, right? Like, I think if it's not embedded, then yeah, then you can ride on all the nice perks that we have of computational capabilities, of connectivity, and all those things. So,
Yeah.
That is where the key question is. Like, without those guarantees or assumptions that we have, how can we operationalize all of this?
Yeah. That's very, because in GameMail we see a lot of papers in the federal learning community that so we can have the kind of wireless communicated to connect the multiple embedded device, more IoT devices. But from the perspective of practical deployment, do you think it's kind of the feasible?
That's why I'm skeptical. That's why I'm skeptical about it. Not the technology. I think the technology is awesome. The work that people are doing is very exciting. It's just that when it comes to the practicality and you look at what the needs really are in the field, then you find that it's not as practical because, even if you use LoRa or Sigfox or whatever, sort of low power communication methods, people are budgeting these long lifetimes in these devices on that assumption of using those low power technologies, right? It's not Wi-Fi by any means, because that's not even an option, right? So given we're already using low power, comm channels, comm methods, and coupled with the lifetimes that we're talking about, and the fact that, they're budgeting 50% kind of tells you roughly that, okay, there is no way I can do all this fancy system optimization. Algorithmically, it's great, but from a system standpoint, I think once it meets the metal, I think it's difficult.
Yeah, I agree with that. Yeah.
Again, I'm not saying we shouldn't do the work. I'm often just like, it's good for us to kind of focus on the research, do the work, come up with these algorithms, and maybe someday, somewhere, we make an intersection, right? And that's the essence of research, right? I mean, if the folks who did all the deep learning stuff back in the day, when they were being told, nah, why is anyone working on this? It's a small little community of people looking at this neural network stuff. Yeah, if they didn't do it, we wouldn't be, having all these talks, right?
Yeah.
When the GPU technology intersected, yeah, then suddenly everything took off. So you never know, right? So therefore, I like to think as researchers, we just keep doing what we are excited about. And you never know where that connection is going to be made.
Yeah, and because I think one major reason for so many people try to promote the on-device training is about the data privacy, right? They don't want their data be sent to the central cloud and so on. So do you think that kind of the third role, the solutions that we can have a good balance between the energy efficiency and such data privacy?
I think the data privacy kind of thing makes sense, like in the context of like, a computational hierarchy that is local, right? Like that's local to you. In other words, it's your smartphone and it's on some dedicated enclaves that you're guaranteed about, right? And so, yeah, so if I have a smartwatch that's talking to my smartphone, which both will more than likely end up being close to each other, right? I think that's an interesting paradigm. So, quote unquote, on device doesn't have to be on device, right? Like, it's just a paradigm of on-device training, meaning like, yeah, the device model at the endpoint is running, so it's personalizing itself. And yeah, so it might leverage the fact that your smartphone has a much better charge cycle, right? Why would I not want to do the computation on the quote unquote the retrain on the smartphone if at night it's already plugged in, right? Then be able to do that. Again, like I think that all is great, but I worry about the fact that when it comes to life, like you have to know what the models are doing, right?
Yeah.
Imagine if like if you have a company and you're quote unquote providing a service based on some ML thing, right? And it's like tail latency gone wild. You know, it's like in traditional server systems, right? When we say, okay, the long tail, right? You have to optimize for the long tail. We worry so much about it because when you scale it out to, you know, billions of users, you've got a serious problem because it's constantly, someone or the other is kind of constantly getting shitty service, right? Because it's just law numbers, right? So like, let's take keyword spotting. Imagine like you do some kind of fancy little, you know, on-device training for keyword spotting, which is deployed on, you know, billions of devices, right? I mean, if asking you, would you be okay not knowing how that model is performing at the endpoint? Because all of these devices are all tweaking something or the other at the endpoint. So you as a person have no clarity about what the model's really doing because you can't reproduce that in the lab.
That's a very interesting point.
That's what the question I have is like, you have this, like when you deploy things at scale, you really have to understand what's happening in the field, right? You can't just push something out and say, oh yeah, you do some localized training, that's great.
Yeah,
a good example of
this, yeah.
A good example of this is something that we've actually seen before, where in data centers, for instance, we were all building up all these mechanisms as microarchitects, you know, coming up with DVFS and doing all kinds of crazy local optimizations that were all happening within the microprocessor, right? Yeah, but if you go talk to supercomputer people, they actually really dislike those kinds of things because they want to have global control, right? They want to know if I send a certain task down to this particular processor, how long will it take to run? But if I'm doing DVFS and all this stuff and I'm mucking with the latencies all over the place, then no two systems have any predictability in terms of the performance. You have performance variability. So one of the first things that we've all done is like, well, let's switch off DVFS because I don't want unpredictable behavior inside the localized things. I want predictable behavior at the big scheduler level. That's because you have, you know, a few tens of thousands of these processors all working independently. So you need to have some sort of statistical distribution that you're confident about. Not like every single time I schedule it, I get a totally different result. Right? So the point that I'm making is like, you know, this is why like people say like, okay, I don't want those low-level optimizations, right? We've seen this happen over and over before. It's just in the context of ML, it's like now it's not controlling a processor's frequency and voltage, but you're basically controlling its outputs, right? And there are differences in the outputs. And I think that's very dangerous, especially in some contexts, the way these machine learning models are being used. I don't think I would want an autonomous car doing on-device training. Let me just kind of put it that way. Maybe you'll get an autonomous car that is doing on-device training, but if I was putting a car out, I'd rather know that there's one network that I've trained that all cars are behaving in a certain predictable way. So if something goes wrong, I can actually be held accountable because if that scenario was presented, I can at least try and dissect it very carefully. Versus saying, oh, car X and car Y, I don't know, they did totally different things under the exact same conditions because the networks were slightly tweaked. So I get very riled up about this point. So
your point is very, very inspiring. Yeah. Yeah, especially I like your example that to interpret it as kind of what we have seen before in the computer system. Yeah, I think that's a very interesting perspective. Yeah. Thank you. And any other questions from the audience? Okay, so if no more questions, let's thank our speaker again. So thank you, Vijay. So this is a very, very inspiring and interesting talk. I appreciate a lot. And
thank you. I really appreciate
our talk. Okay, and
thank you, Professor.
Thank you. Thank you.
Well, appreciate your time. Have a good one.
Have a wonderful day. Thank you. Thank you, everyone, to attend our today's talk. See you. Bye.